Hi, I'm Ron Kerr with Houston Seismic. I'd like to talk today about a seismic program from 2021. It was done for commercial and research purposes. It's a 2D seismic line from South Dakota in the northern United States. Client data owner is Near Surface Observations, James Mika. This was believed to be the first seismic program project in the area, and that sneak peek at some of the final results there on the right. And I'm going to cover a little bit of the how and the why it was acquired, some of the specifics of the acquisition and the processing, and then some of the final results. So I mentioned Near Surface Observations as a data owner and client, James Mika, and it was a collaboration with three principals: Alan Chatenay with Explor, who was in charge of the seismic acquisition; Bill Wepfer with Eskaton Seismic, in charge of the seismic processing. And again, I'm Ron Kerr with Houston Seismic, did some consulting on it. The project objectives were both for commercial and research purposes. Commercial goals being to increase revenue, obviously, and to generate money, and also geothermal is a new our source for energy and heating for both agricultural, aquaculture, and home and domestic use. Groundwater sources for irrigating crops and livestock, and also home and domestic use. And the researchers who are working on this data set include the South Dakota Geological Survey, Castillo Geophysical, and Delft University of Technology. And I'll talk later about the specifics of ongoing research. Now there's the location where the data was acquired in South Dakota, the northern Great Plains of the United States. The line is located approximately at that arrow. Looking down on the state of South Dakota, this is a Google map view. You can see to the far west are the famous Black Hills of South Dakota, and labeled there the Missouri River. The acquisition of the seismic data was just to the east of the Missouri River at the yellow arrow. This is in the Kennedy Basin, geologic basin, on the eastern margins of the Kennedy Basin. The surface terrain is rolling agricultural. The near surface just below is approximately 100 to 300 feet of ice age glacial drift. That's approximately 30 to 90 meters. And below that glacial drift is believed to be approximately 800 feet or 250 meters of Cretaceous sediments. This includes sandstone, shale, and limestone. The seismic acquisition was done by Explor, Alan Chatenay. This was in August of 2021. Single 2D line. The energy source was the Explor Pinpoint, very mobile, easily deployed source point. The receivers were 3-component, recording in the XYZ direction using stride nodes. Now every 10 feet was a source interval, that's approximately 3 meters, and every receiver interval, also 10 feet. They were interleaved, so every 5 feet alternated between a source point and receiver point. And these went for a total line length of 1 mile, or approximately 1,600 meters. Data were recorded for 4 seconds at 2 mil sample interval. Here's a satellite view of the project layout location. The 2D line is shown in red, running north-south for the 1 mile distance. You can see the farmhouse there on the northeast corner in this agricultural area. All receivers were active during the shoot as the sources went from one end of the line to the other. Now if you notice there in the south central area there are some green dots. Those are additional receivers, passive receivers, that was being done for another research project, but I will not be talking about that today. I'm only talking about the single 2D line shown in red. This is a LiDAR image showing the elevations. LiDAR is a laser generated elevation technology. LiDAR stands for light detection and ranging. The 2D line is shown in blue here, running north-south, and you can see that there is approximately 20 feet or 6 meters of topographic relief along the seismic line. The relative elevation lows are in green and the relative elevation highs are in red. And if you notice to the south, there is a localized high region, and that is believed to contain potentially aggregate glacial deposits from the Ice Age. That will come into play in the imaging of the seismic, as we'll see later. Here's the acquisition equipment arriving on site, very mobile, just a small truck and trailer pulling all the equipment. This is the survey navigation equipment setup, the base station, global navigation satellite system. It supports real-time kinematic positioning, which is really needed for the dense acquisition. I mentioned every 10 feet was a new source point and 10 feet was a new receiver point. So the surveying determines the X coordinate, the Y coordinate, and the Z elevation for every source and receiver. On the left is the Explor pinpoint source, energy source. You can see it there at by the left foot of the gentleman. That looks like a runner's baton in a track meet. Quite easily portable. Just goes in the ground and generates a energy signal for the seismic. On the right are the layout of the 3-component stride node receivers, and they record the earth movement in X, Y, and Z. It's simply spiked into the ground to hold it in place. So the pinpoint source goes off and the energy and reflections are detected with the stride receivers. So after acquisition we got the field data as seen here. Up at the top is a raw shot gather. There are 508 traces, or the entire 1 mile of the line running horizontally, and the time axis is running vertically. You can see 200 to 400 milliseconds, and we'll talk about this raw shot gather later. And at the bottom is a field QC brute stack. Gives a rough idea of the geology. This was done just for QC purposes, and we will move on to full processing next. Seismic processing workflow was also done in 2021. This was by Eskaton Seismic, Bill Wepfer, and you can see there the highly detailed processing flow. Quite a few routines run. The highlights include refraction statics, residual statics, a lot of denoise, including their SCORE denoise or noise reduction technology, and Prestack time migration. Let's go over a few of those. Here's that same raw shot gather that was shown earlier. We've highlighted there in arrows and labels some of the key events you'll see on this shot gather, including the direct arrival, which is directly from the source to the receivers along the surface of the Earth. Some of the noise that's generated commonly with land data, source generated, ground roll, air wave, what have you. And then you can see the primary events. There's a number of them. These are curving down away from the source point. These are the events we want to see, and they're believed to be Cretaceous reflectors in the subsurface. Here's a shot gather that has been partially processed, but not completely. And this is, you can see highlighted there some of the remnant noise that still remains, the ground roll and the airwave in particular. Now this is before the Eskaton SCORE noise reduction technology. After the noise reduction, you can see that the ground roll and the airwave noise are greatly reduced, and that helps leave the primary event, what are believed to be Cretaceous reflectors, looks a little bit nicer and cleaner. And from here we are going to look at stacks from here on out. This is a preliminary stack before application of the refraction statics. Refraction statics helps remove effects of elevation and near surface velocity variations. So you can see the reflectors below, especially at 200 and 300 milliseconds, but they're a little bit up and down and wobbly. After the Eskaton application of refraction statics, you can see the events look a little bit better. And this is a midway event, or a step in the processing flow. Let's go a little bit further. And this is after additional score noise reduction, residual statics, and frequency whitening of the wavelet. Looks better still. And next will be the Prestack time migration. Here's the Prestack time migration routine. Looks better still. North is to the left, south is to the right. You can see the Cretaceous events running from about 70 or 80 milliseconds in the section down to approximately 300 milliseconds. The strong event at 300 to 350 milliseconds is believed to be the Precambrian basement. And if you notice there on the right side of the section, there is a zone of reduced signal to noise fidelity right in here. That is believed to be the location of the Ice Age deposited glacial aggregate. Remember from the LiDAR image shown earlier, that's a localized elevation high, and we believe that there underlies some glacial aggregate. Now what that does is it disperses the seismic energy, making the signal much less and the noise much higher and much harder to image. Here's the same section but in a color display. Many people prefer to see seismic data in color, so we've included that here. This has been deemed a successful project, and below are comments from the client operator, Mr. Mika from Near Surface Observations, talking about the acquisition. He said, quote, "The dataset was acquired efficiently and safely with no HSE recordables and appears to be of very high quality." Regarding the processing, he said that data responded very well to a robust land processing sequence and possesses frequencies in excess of 150 Hz. On the interpretation, images possess strong reflectivity throughout the Cretaceous section, down to and including the top of the Precambrian basement. Of commercial interest, major groundwater aquifers, including the Dakota sandstone, appear to be well imaged. Additionally, there is strong evidence of buried channels, aquifers, and potential shallow aggregate zones, which is another economic target in the glacial overburden. I talked earlier about the continuing studies, so follow-up work is ongoing and includes surface wave inversion, shear wave imaging, and integration with that passive seismic survey that I showed earlier, the green reflectors in the earlier slide. Green, nodes. So let's summarize here. In the top left is the field concept, the location in South Dakota, and there you can see the receivers laid out, the stride nodes. Top right is the raw data that was acquired in the field, and at the bottom is the migrated final stack, courtesy of Eskaton, after Explor acquired the data. Thank you very much. For further correspondence, I highly encourage you to email one of the participants. Near Surface Observations at the email shown there, Explor for the acquisition at the email shown there, or Eskaton Seismic for the processing at the email shown there. And again, I'm Ron Kerr with Houston Seismic. Feel free to email me as well. Thank you very much.